Okay, so in this video, I will be explaining the general flow of data as well as some more details about the code that we are using in the ROS side of the project on the Jetson. So first, we'll talk about how the general flow of data is throughout the project. So I've already talked in another video about how we send data to the Jetson on STM32. This was in the video about the communication protocol. And I talked about how we create the packets that we are working with, how we send them through the CAN bus network. And also, I explained how we receive the data on the microcontroller. So I gave an example with the server thread here, where there was a function for receiving the data, and which was the handle rotate, which is a callback function that is defined in the server thread and is called whenever we receive a server packet on the CAN bus. And I also explained how to send data through the CAN bus. So now, on the Jetson side, how do we work with the data that we've sent from the microcontroller? So here you have a very simple schematic, just so you can understand in general how this works. So let's say that we have two nodes, or three in this case. We have the Jetson, which is one of the nodes in the CAN network, and has as an address 0x0000. So this is an hexadecimal. Then let's say that we have two other nodes. So we have one STM32 nodes. So this is one of our Orion nodes. So this board, if you remember. And let's say that we've configured here the dip switch to have the OX0001 address. And we have another node which is also connected on the CAN bus and is actually the last node in this case. And we've set it as the node with the ID number 2. So just remember that this node and this node, being the first and last nodes in the network, will need a termination resistor. So they are the last node in the bus. So it means that we will need to set this switch here to the termination side so that we can add a termination resistor to the bus. Okay, so we have this setup here. And now what happens when we send data from the microcontroller to the Jetson? So the following happens. Let's say that we want to send a voltmeter packet. So this is a packet from our Roco package here. So I can go in the Broco library as usual, and you can see in the protocol 23.h the different packets. If I look for voltmeter packet, you will see that it is simply a reliable identifiable packet. So as you've seen in the video about the communication protocol, with a single field, which is the voltage. Okay, so it actually does not have a single field, as you remember, because if it's a reliable identifiable packet, then it will also have a CRC at the end and also a packet, an ID for the sender ID. So these are two additional fields that are sent along with the packet. Okay, so the packet contains the sender ID, of course. So we send this data through the CAN bus and we give it the destination ID equal to 0x0000. So this is our destination ID to which we want to send the data to, so to the Jetson. Okay, so what happens when we do that? So we send the data through the two CAN buses, so through the CAN bus number 1 and number 2, which are basically this on these connectors here, but also on these connectors here. And what will happen here is that we will need to run two nodes on our network. So we will run the Roco-ROS interface on the CAN 0 of the Jetson, which is connected to the CAN 1 of the STM32. And we will have a node that is connected to the CAN 1 of the Jetson, which is connected to the FD-CAN2 of the microcontroller. Okay, the indexes are different because the Jetson has CAN0 and CAN1, and the STM32 has CAN1 and CAN2. So these are nodes that are running in our ROS package. So if you're not familiar with ROS, when we have a package, we can run executables, which are actually programs, and these programs are called nodes, and they can be run like in parallel. So in this case, we will run two nodes, which are the Rokoros interface, and one of them will run with the CAN0 as an argument, and the other one with the bus CAN1. So the goal of this interface here is to convert our packets that are sent on the bus to ROS messages. So if you are familiar with ROS, you know that it works with publishers and subscribers, and we have to define a certain type of data and a name for a certain subscriber so that we can publish the data onto that topic. So this node on CAN0 here will publish on a topic whose name is defined like this. So we'll have the topic EL/voltage, EL because it's electronics, and voltage because we are sending voltage. And it will be preceded here by the name of the bus on which it is connected to. So we will have actually two topics, one for the CAN0 and one for the CAN1. So these two topics correspond, of course, to the data that we've sent on the FD-CAN1 and the FD-CAN2, because we are sending the data on the two buses at once, so that we can have some redundancy and we can choose which bus to get the data from in case one of the bus fails. Okay, so we are sending these two data, and then we need to choose the data that we want. So to do that, we use another node here, which is the avionics mux node. And this node chooses between this data stream and this data stream, and then chooses the one that is the most logical, so the one whose bus is currently valid, and will publish on a final topic here, whose name is just /electronics/voltage. So this is the whole flow of data that we have. And now the question is, how does the avionics mux choose the data here? So what it does is it uses another topic, which is given by this. And this topic here is just a list of Boolean information. So we have 16 Booleans, and each Boolean here corresponds to a node ID. So why 16? We say 16 because our dip switch here has 4 different positions, which means that we can go from 0 to 15 if we do all of the binary combinations. So in this case here, in this screenshot here, we see that node number 0, 1, 2, 3, 4 is valid, whereas all of the other are false. So this is just one of an example. So let's say that instead of being 2, this is node number 4, for example. And then let's say that the CAN0 is equal to this, and the CAN1 we have something else, but let's say that everything is false here. Then we know from this topic that the node number 4 is valid, and that and if everything is false here, then we know that the node number 4 is not valid on the bus CAN1. Okay, so each bus will publish will always publish the states of each of their nodes, so that we can know whether or not the node is connected to the bus. And depending on which bus the node is connected to, then we choose the bus, and we publish the corresponding topic. Now let's say that both are available. So if we have that the node ID number 4 is available on CAN0 and is also available on CAN1, then how do we choose which topic to publish? So in that case, in the code, I've written that we just prioritize the bus number 0, and we will publish this one. Okay, so this is just a quick example of how the data goes from the microcontroller to the Jetson while keeping the redundancy of the bus. So again, I will do another summary. So it sends the data, the Jetson gets it, converts it to a ROS topic on 2 topics, and the avionics mux is in charge of choosing which topic to publish in the end. And to do that, it will choose it from another topic which keeps track of the states of the nodes on the bus. And how does it keep track of the state of the nodes on the bus? It will use another packet, which is a ping packet. So the Jetson will periodically send pings on the 2 buses to the microcontroller. And if the microcontroller responds in time on the bus, then we know that the microcontroller with that ID is present on the bus. So how do we know it? We know it because the packet ID for the ping packet also contains the packet also contains the ID of the sender. So imagine that the Jetson sends a ping request to every microcontroller. Then the microcontroller here will send back a ping with its ID, so 0, 1 for this one or 4 for this one, to the Jetson. And the Jetson will receive it and know that this node here is on the bus or not. Like if it doesn't receive anything after a certain time, it will know that the node is not on the bus, and it will set the corresponding field here in the node state to false. So this is the general idea of our redundant system. So this was just one way from the microcontroller to the Jetson, but the other way around is very similar. So I didn't do the schematic here, but the other way is very similar. Let's say that you have some kind of request that you want to do from the Jetson to the microcontroller. So what you will do is you will publish a message on the topic that you want to send to the microcontroller. It could be, for example, some configuration request or some or for example, to rotate a servo, as we've seen before. So we would have a topic whose name is, for example, let's say it's EL servo request. This servo request here will go through the avionics mux. Then, depending on the state of the nodes here, it will choose on which topic it wants to publish. So there will be 2 topics here, which will be CAN0 servo request and CAN1 servo request. Okay, so CAN1 servo request. So this will be the other way around. Then it will choose to publish on either this one and this one. So let's say that it publishes on the first bus here. So it will publish here. And then the Roko-ROS interface will convert it to a Roko packet. So it will not be a voltmeter packet, but it would be, for example, a servo request packet. And it will send it to the microcontroller, which can then call the corresponding callback function. So we've seen here in the code that our callback function in this case was the handle rotate function, which receives a servo packet. So it's not actually a servo request packet, but just a servo packet. And then it will perform its actions. And in this case, in the code, in the handle servo here, we also send back a response. So imagine the servo response here will do the same thing, but the other way around. So the servo response will be sent through through one of the bus, actually. So let's look at the code here. So it will know on which bus it was received, and it will send the data back to the same bus if it's a response, so that we don't overwhelm the bus. So it will send, if it has received the request on FDCAN1, then it will send the response back on FDCAN1, and then it will go through this. Then we know that it is available on FDCAN1, so it will go through all of this and send the request. So like the flow of data is very similar in both ways, but you just have to know that there is a node here that chooses between the 2 types of data, and there is a node here that converts the Roko packets to ROS packets, and this is the Roko-ROS interface. Okay, so I think this is it for like the general idea of for the flow of data. So yeah, I will give you now a practical example for how it is in like on the Jetson and what you can actually see in reality. Okay, so in this video, I will just do a voiceover of a recording that I did on the Jetson. So I have already connected the board to the Jetson, and I will show you a practical example of how we actually read the data on the Jetson. So at the end of the video, I will probably just have a small video for the setup and how I actually connected the board to the Jetson. Okay, so first let's go inside of the desktop and electronics workspace, and we need to launch the command source I, which is a shortcut to install all of the or everything that we need so that we can have access to the custom messages of our ROS package. Then I will launch the command that can start the package. So the command is as follows. We launch it for the package avionics main, and we launch the launch file, which is defined as avionics launch.p.python. Okay. Here we can see that it tries to connect on CAN 0 and CAN 1, and it has successfully connected on the two buses. I have started here another terminal so that we can have a list of the different nodes that are running. So as I've said during the overview, you can see that we have two nodes for the Roku interface. We have one running on CAN 0 and one running on CAN 1. We also have the MUX manager here, which is also part of the avionics MUX. And this is the one that will choose the data from which we will publish on the final published topic. So here I can do a ROS topic list, and you see that every topic is duplicated between the CAN 0 and the CAN 1. So you have the duplicated topics as well here as the final topics. Okay, so here you can see here the /el/imu, and if you go down, there is also the CAN 1 /el/imu and the CAN 0 /el/imu. So yeah, it might have been a bit too fast here, but it should be somewhere here in the code. Yeah, well, in this case, it's /el/mu data, the final topic that we are looking for, and in the code here, it's this code here. So you have CAN 0 /el/imu data, and we have the same thing for CAN 1. Okay. Now I will just try and echo the node state that I was talking about before. So this is for the node state on the CAN 1, I think, if I saw this correctly. Yeah, it's on CAN 1. So you can see here that only one node is connected and the ID is equal to 4. And now I do the same. So I will just echo the node state for the CAN 0 so you can see. So I've connected the two buses to the Jetson, which is why we can see the node on the two buses. Okay, and I will also echo the actual data that we want. So I will just echo the IMU topic. So if it's not clear, the actual topic at the end of the multiplexer is emu_data, and the emu here is the output of another node, which I talked about before or maybe I will talk about in this video, but it is the output of the avionics converter, which actually gets as an input the emu_data and outputs another data with another type, so that we don't have to use special messages from like custom messages from ROS. Okay, just a change of type of data basically. So here I'm just doing an echo of the IMU, and you can see that we can read the data perfectly. So I have just plugged in the data, the IMU actually. And you can see here that also sends the configuration data. Okay. So now I just want to show you what can be seen on the CAN bus. So on the Jetson, we can write here CAN dump, then the name of the CAN and just the end symbol, and you can see everything that goes through the CAN bus. So for CAN 0, this is what we see. And I will do the same for CAN 1. So you can see that the data from the microcontroller is correctly sent through the two CAN buses. And so then what we can do is, so here, for example, okay, I will just skip a bit. Okay, so here we can see that the node is true and true, so it's still connected. Here we have the CAN 0, which corresponds to this, and the CAN 1, which corresponds to this. And you can see here that I've unplugged the connection. So it was the connection of the FD-CAN 1 to the Jetson, which is why I don't receive any data. And here it will detect that the connection has been, well, disconnected, so it now returns false. But even if it's false here, you can see that the acceleration is still sent through the bus because now it is choosing this data. Okay, so now I've reconnected it, and I can do the same here. So I've just disconnected this, the sensor on this bus. So now it is only connected to CAN 1. And you can see here that the data has started to go again, and that it has detected here that it is no longer connected. So now it is choosing the data from the CAN 1 instead of the CAN 0. So this is how the multiplexer works in practice. It will choose between whichever bus is available at the moment. Okay, so this was just a practical example, and I hope it made it a bit clearer on how it is used in practice.